Okay, so now we're going to talk a little bit more about fatty acids. Just to remind everybody, this was kind of this categorization of lipids, and our classes of lipids were steroids, waxes, triacylglycerols, glycerophospholipids, and sphingolipids. Um, the four latter that I just talked about were all components that contain fatty acids. So actually, before we go into talking about waxes and triacylglycerols, et cetera, we're going to just talk about features of fatty acids, and then we'll kind of move on to the more complicated classes of lipids. And one of the main things we're going to talk about is saturation, and they have this like what I think is pretty funny chip analogy going on, and I'll explain a little bit more about that. But yeah, let's wait until we get to there. So first of all, what is a fatty acid, right? So they're long, unbranched carbon chains, so that's important, right? So long and unbranched carbon chains with a carboxylic acid group on one end. They are quite long, 12 to 18 carbons long. Because that's such a huge, even though that carboxylic acid end is polar, that's such a huge carbon chain that they are going to be insoluble in water. Two very important designations that we're going to talk about over and over and over again in this chapter is this designation of being either a saturated fatty acid, which does not contain any double bonds, or an unsaturated fatty acid, which contains double bonds. Okay, so when you hear about a saturated fat, that means that there are no double bonds, so all single bonds going on. Unsaturated fats, unsaturated fatty acids, means that there are some, either one or more double bonds going on in there. Okay, when we represent our fatty acids, so first of all, if you were a fancy computer program, we got this ball and stick kind of structure. Here's our carboxylic acid. Here, that was terrible. Here is that long hydrocarbon tail end. There are different ways to represent, well, so first of all, then there's this expanded, well, the line angle formula, which we're used to sort of seeing, but again, you can see this huge carbon tail, or the condensed formula, right, where you write out the different carbons explicitly. You don't draw the carbon-hydrogen bonds, but you draw all the carbon-carbon bonds. So those are the two forms that we're used to. Because they're such long chains, there's another sort of shorthand that we use, and I don't even know, I mean, I don't know what this would be called, the condensed something, I don't know. But anyways, what it is it says, let me just help sort of match what's going on here. So this is the carboxylic acid group. You can either write that just like the carboxylic acid group. Another way of doing that is COOH. That's another way of stating carboxylic acid group. On the end, we have a methyl group, right? That's that terminal carbon right there is a methyl. And in the end, or in the middle rather, we have CH2, 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 CH2. So one of the ways that they draw this in an even more condensed sort of formula is by having CH2 and then the number of times that unit repeats, right? So here it went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different units of CH2. So that's how they got to this CH2 in parentheses 10. Okay, so because we're talking about such huge chains, in order to save space, these forms are often what you're going to see, these sort of like condensed structural formulas. Okay, let's take a look at some saturated fatty acids. So these are these names. We're not going to memorize structures just like we didn't do with our carbohydrates, but I want to show you what you're going to be given on an exam, and what you're going to be using when you do your homework is a chart like this, right? So I tell you the name of the fatty acid. This number here, the first number is the number of carbon atoms, and the second number, so the number of carbon atoms, the second number is the number of double bonds, and then you have both the condensed structure. I'm going to call it the condensed structure. I don't know. As well as the bond line structure for what that fatty acid looks like. So while you're not expected to have memorized all the different fatty acids, this is a table that you should be familiar with and good at using in your homework, right? So my intention is when you go to do your mastering chemistry homework or whatever, this is the chart that you use in order to solve those problems. This is what you'd be given on an exam and asked to do similar problems. Okay. All right. So now let's look at just just the saturated fatty acids from that. Meaning that when I'm looking at the number of double bonds, each one of these have 0 double bonds because it's a saturated fatty acid. Okay. And what we're going to see is as we increase in the number of carbons, so we increase that carbon chain, the melting point also increases, right? So this is an increase in the number of carbon atoms, and we see an increase in the melting point. The other thing I want to point out about these melting points is they're all well above 0 degrees Celsius, or even 22 degrees Celsius, so well above room temperature even, which is about 22 degrees Celsius. Meaning that your melting point's higher than room temperature. That means that these are all solids. Where can I write this? Solids at room temp. So saturated fats are solids at room temperature. There's really no rhyme or reason, or at least not one that I know of, behind the naming of them. Lauric acid, myristic acid, palmitic acid. I mean, clearly palmitic acid is because it comes primarily from palms. But, you know, again, we're not here to memorize the name of all the different fats, but we're going to see how the names are used later. And so we need to be able to sort of like go to our chart and figure out what they're talking about. All right, now let's look at some what are called monounsaturated fatty acids, meaning that the number of carbon-carbon double bonds is just 1. Okay, these all have one double bond in there. So actually, let's zoom in on one of these guys. Okay. Let's make sure that we can sort of understand what's going on between the condensed structure and the bond line structure here. Okay, first of all, boom, boom, they got a double bond, right? So that's how we know that it's an unsaturated fatty acid. There's only one of them, so that's what makes it a monounsaturated fatty acid. But I want to go through and color coordinate carbons just so we know what's up here. So this, my carboxylic acid group, that would correspond to this here. Okay. Then I have 7 CH2 units. So 1, 2, 3, 4, 5, 6, 7. Then I get to my double bond, right? So that takes care of these two. Now on the back half, I have another 5 CH2 units. So 1, 2, 3, 4, 5, before finally getting to my methyl group at the very end. Okay, so hopefully being able to decipher that condensed structure, you guys can figure that out. What else was I going to point out? Oh, the other thing that I want to point out is that number of carbon atoms, 16, okay? That includes all the carbon atoms in there, including that carbonyl carbon. And the reason I want to point that out is because there are going to be some mastering chemistry problems where you have to draw these structures. It's going to be like, draw linoleic acid or something like that, right? And so you want to make sure that you actually have all the correct number of carbons. So again, this one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. When it says that there are 16 carbons, it means all the carbons, including that carbonyl carbon. So don't make sure you don't forget to count that when you're building your structures. Okay, and so as we can see, sort of similar trend to what we saw before, as we increase in number of carbons, so we go from 16 to 18, we also increase in our melting point. Both of these are below room temperature though, right? So even with just 1 degree of saturation, we have gone from being a solid at room temperature to being a liquid at room temperature. God damn it. All right, well. Okay, so just that one double bond, that one introduction of 1 degree of unsaturation has taken us from being a solid at room temperature to a liquid at room temperature. And so let's look at our constants page and see if we can't hammer this point home here. Let's look at stearic acid and compare that to oleic acid. Okay. Both of these have 18 carbons, but oleic acid has 1 degree of unsaturation, whereas stearic acid has 0, is saturated basically. Okay, so let's go and see melting points. Compare melting points. Oleic acid has a melting point of 0 degrees Celsius, so 14 degrees Celsius. So you have to be below 14 degrees for it to be a solid. Whereas stearic acid has a melting point of 69 degrees Celsius. Okay, so it's a solid all the way until you get to be 69 degrees, and then it will melt, right? So that's a pretty big gap just by introducing that 1 double bond. And then if I go to a polyunsaturated fat, then it becomes even more dramatic, right? So again, 18 carbons. Now I'm at a melting point of -5 just by introducing 2 double bonds. If I introduce 3 double bonds, I'm at -11. Okay, so the more double bonds you have, the more unsaturated your fat is, and thus the lower the melting point's going to be. It also depends on number of carbons. Okay, yeah. So then these are just again varying degree or examples of our polyunsaturated fats, which contain 2 or more double bonds. All right. Now, if you remember back from when we were talking about double bonds, we can have 2 different stereoisomers, either trans or cis. These have a pretty big effect on the overall shape of a fatty acid, right? We're used to seeing them all in those extended chains when we draw out all of our single bonds. Well, if you have a trans fatty acid, it maintains that shape pretty similarly, right? Because of the orientation of a trans double bond, similar to if we had no double bonds at all, kind of just that straight chain thing going on, right? If you have a cis double bond, there's a significant kink in your fatty acid that changes the overall shape of that fatty acid, right? So a trans fatty acid is mostly just a straight chain, whereas a cis fatty acid will have a big old kink in it that leads to, you know, kind of V shape in your molecule. This has a big effect on the melting point, okay? Because what the melting point is all about how much those chains can pack together, right? So for a saturated fatty acid, those chains, because there's no sort of degrees of unsaturation, they can pack together really, really highly, and thus they form strong intermolecular forces, what are called dispersion forces. Okay, so I don't want to go too far into it, but these are the type of forces, as opposed to like hydrogen bonding or dipole. Dispersion forces are the type of forces that happen between non-polar molecules. They have a lot to do with surface area. So since these things are so long and they have so much surface area, they can pack together really tightly and form strong intermolecular forces, which means that it requires a high temperature to separate them or to melt them. For unsaturated fatty acids, so this is this chip analogy that we were talking about before. The saturated, as well as to some degree the trans unsaturated fatty acids, they can stack together really easily. When you have, so your saturated fatty acids, they stack together really well, like a can of Pringles, right? Where you're putting those chips one on top of each other, the shape's fitting perfectly, and so they don't take up very much room at all. When you have a unsaturated fatty acid, right, and it has this cis kink in there, that means that these molecules can't really stack together very easily. So that's why you get this sort of this loose pile of chips that have a lot of air in between there. And what that translates to on a molecular level is this idea that they can't pack closely together. They have weaker dispersion forces and thus lower melting points. Okay, especially prevalent with these cis fatty acids. Although when we talk about unsaturated fatty acids, you always have a mix of cis and trans. It's the cis that are really leading to the way, way lower melting point that we see. Okay, so here we have a particular acid, this fatty acid. This actually I don't think is one of the ones that they gave us here, right? So again, this is one of the skills that we want. Sorry, clean this up. This is one of the skills that we want, is given a new fatty acid, can we analyze it based on what we know? So why is this substance an acid? Well, because it's got this chunk right here, right? This carboxylic acid end. How many total carbons are there? So let's make sure we know how to count carbons. We're going to include that carbonyl carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is it saturated, monounsaturated, or polyunsaturated? We can see that there is a single double bond right here, so this would make it monounsaturated. And because it's unsaturated, we're going to expect it to be a liquid at room temperature. Would it be soluble in water? No, because they're never soluble in water. Lipids are never soluble in water. That's one of the main characteristics of a lipid. This is just kind of why human beings use fatty acids, in addition to being very key things like insulating our organs, protecting our organs, forming main parts of nerves, and all that good stuff. It's also used as a storage of energy. So when you have an excess of carbohydrates in your system, our body will convert those carbohydrates into fatty acids and store them, and then pull from that storage later in order to generate energy. When we do synthesize fatty acids, they're mostly saturated fats. So the fats that our body make are saturated fats, and they're there for storage. Unsaturated fats usually come from plant sources.